Hello there, and welcome to the Sleepy Library. Tonight, we're going on a peaceful journey deep into our planet, traveling through layers of rock and metal that stretch thousands of miles beneath your feet. A quiet exploration of the hidden world that exists below the surface we walk on every single day. So, settle in, let your breathing slow, and prepare to descend into the warm, ancient heart of Earth itself. Imagine standing on solid ground, the sidewalk beneath your feet, the grass in a park, the floor of your home. It all feels permanent, unchanging, reliable. But beneath that thin crust of rock lies an entire world, vast and dynamic, filled with slowly churning stone, liquid metal, and mysteries that scientists are only beginning to understand. This hidden realm makes up most of our planet's volume, and it's far stranger and more fascinating than most people realize. Every step you take is a step on the outermost layer of an immensely complex system. Beneath the concrete, beneath the soil, beneath the bedrock, there are layers upon layers extending almost 4,000 miles down to the very center of our world. These layers have different compositions, different temperatures, different behaviors. Some are solid, but flow like thick honey over millions of years. Some are liquid metal, churning and swirling like a vast ocean. And at the very center lies a ball of solid iron under such extreme pressure that it remains frozen, despite temperatures that rival the surface of the sun. Tonight, we'll travel through all of these layers together. We'll start at the surface, where we live and work our way down, mile by mile, discovering what each layer contains and how it behaves. We'll learn about the forces that shape our planet from within, the slow movements that build mountains and open oceans, and the invisible magnetic shield that protects all life from the harsh radiation of space. It's a journey no human has ever physically made, and no human ever will. But through science and imagination, we can visit these hidden realms and understand them. Before we begin our descent, let's consider the scale of what we're about to explore. Earth has a radius of roughly 3,900 miles from surface to center. That means if you could drill straight down through the planet, you would travel nearly 8,000 miles before emerging on the other side. Most of this journey would take you through regions that are intensely hot, under crushing pressure, and composed of materials behaving in ways that would seem impossible at the surface. The deepest hole ever drilled by humans reached just over 7.5 miles down. That's the Kola Superdeep borehole in Russia, a scientific drilling project that took nearly 20 years to complete, from 1970 to 1994. The Russians chose a location on the Kola Peninsula in the Arctic Circle and began drilling, hoping to penetrate deep into ancient continental crust and learn about conditions at depth. They encountered many surprises along the way. The temperature increased faster than expected. The rocks were more fractured than predicted. At depths of several miles, they found water-saturated rocks, where conventional wisdom said the rocks should be completely dry. By the time they stopped drilling, they had reached a depth of about 40,000 feet, or 7.5 miles. This was deeper than anyone had ever drilled before, and it remains the deepest today. But 7.5 miles, impressive as it is, represents less than 0.2% of the distance to Earth's center. We've barely scratched the surface. Literally. Everything we know about the deep interior comes not from direct observation, but from indirect evidence. How do we know what's down there if we can't see it or sample it? Scientists use several methods, but the most important is seismology, the study of earthquake waves. When an earthquake occurs, it generates vibrations that travel through the entire planet. These seismic waves travel at different speeds through different materials. Dense materials transmit waves faster. Hot materials transmit waves slower. Solid materials transmit all types of waves. Liquid materials can only transmit certain types. By carefully measuring how long it takes for seismic waves to travel from an earthquake to a seismometer on the other side of the world, scientists can determine what kinds of materials those waves must have passed through. It's similar to how doctors use ultrasound to see inside your body without cutting you open. The sound waves bounce off different tissues at different rates, and by analyzing the echoes, a computer can construct an image. Earth scientists do something similar, using earthquakes as their sound source and seismometers as their receivers. Over decades of collecting data from thousands of earthquakes recorded at thousands of stations around the world, they've built up a remarkably detailed picture of what lies beneath. Other methods complement seismology. Scientists study meteorites, which are fragments of asteroids and occasionally pieces of other planets. Some meteorites are made of iron and nickel and are thought to be pieces of the cores of small planetary bodies that broke apart early in solar system history. By analyzing these iron meteorites, we gain insights into what Earth's core might be like. Other meteorites contain minerals that only form under high pressure, giving us clues about conditions deep inside planets. Laboratory experiments are another crucial tool. Scientists can recreate the extreme conditions found deep in Earth using specialized equipment. Diamond anvil cells can squeeze tiny samples to pressures exceeding those at the core mantle boundary. Laser heating systems can raise temperatures to thousands of degrees. By subjecting mantle minerals to these conditions and observing how they behave, measuring their density, seeing how they transmit seismic waves, and watching how they deform, researchers can test whether their models of Earth's interior are correct. Computer modeling rounds out the toolkit. Modern supercomputers can simulate planetary interiors, modeling how heat flows, how material convects, how magnetic fields are generated. These simulations help scientists understand dynamical processes that would be impossible to observe directly, and allow them to test hypotheses about how Earth's interior has evolved over billions of years. All of these lines of evidence come together, each one constraining and informing the others, to give us confidence that we really do understand what lies beneath, even though we've never seen most of it directly. It's one of the great triumphs of scientific reasoning, using indirect observations and logical deduction to understand realms completely beyond our direct reach. Now, let's begin our descent into the Earth. We're standing on the surface at zero depth. Beneath us lies the crust, the thin outer shell that makes up the continents and ocean floors. The crust comes in two distinct varieties, each with its own composition, thickness, and story to tell. Continental crust is what makes up the landmasses we live on: North America, Europe, Asia, Africa, South America, Australia, and Antarctica. It's relatively thick, averaging about 25 miles, but ranging from about 15 miles in some areas to as much as 70 miles beneath the highest mountain ranges. Continental crust is also old. The oldest known crustal rocks on Earth date back more than 4 billion years, formed when our planet was still young and violent, bombarded by asteroids and comets, its surface covered with volcanoes and lava flows, its atmosphere thick with volcanic gases. These ancient rocks are found in only a few places. The Acasta gneiss in northern Canada dates back about 4 billion years. Zircon crystals found in Western Australia are even older. up to 4.4 billion years old, though these are tiny mineral grains rather than intact rocks. The Jack Hill zircons, as they're called, are remarkable because they preserve information about conditions on Earth when they formed. Analysis of oxygen isotopes in these zircons suggests that liquid water existed on Earth's surface as early as 4.4 billion years ago, much earlier than previously thought. If water existed that early, then perhaps the conditions for life existed much earlier than we once believed. Continental crust is made primarily of granite and related rocks that are rich in silicon, aluminum, potassium, and sodium. These are relatively light elements, which makes continental crust less dense than oceanic crust or the mantle below. The average density of continental crust is about 2.7 grams per cubic centimeter. This might not sound light, but it's significantly less dense than the 3.3 grams per cubic centimeter of the mantle. This density difference is crucial because it means continents float on the denser mantle beneath them, much like wood floats on water. But continental crust isn't just granite. It's a complex mixture of many rock types, recording billions of years of geological processes. There are intrusive igneous rocks like granite, diorite, and gabbro, formed when magma cooled slowly beneath the surface. There are extrusive igneous rocks like rhyolite, andesite, and basalt, formed when lava erupted at the surface and cooled quickly. There are metamorphic rocks like gneiss, schist, and marble, formed when existing rocks were transformed by heat and pressure. And there are sedimentary rocks like sandstone, shale, and limestone, formed from the weathered and eroded remains of older rocks or from the accumulated shells of marine organisms. This diversity reflects the complex history of continental crust. Unlike oceanic crust, which is relatively simple and young, continental crust has been built up, reworked, melted, recrystallized, deformed, uplifted, eroded, and reburied countless times over billions of years. Every continent contains rocks of many different ages, juxtaposed in complex patterns by tectonic forces. Geologists can spend entire careers unraveling the history recorded in a single mountain range, piecing together sequences of events that span hundreds of millions of years. The continents themselves have moved around Earth's surface throughout geological history. About 300 million years ago, all of the continents were joined together in a supercontinent called Pangaea. Before Pangaea, there were other supercontinents. After Pangaea broke apart, starting about 200 million years ago, the continents slowly moved to their present positions, and they're still moving today, at rates of a few centimeters per year. In another 200 million years, they'll be in completely different positions. Some scientists predict they'll eventually come together again to form a new supercontinent. This movement is driven by plate tectonics, a process we'll explore in more depth shortly. But the key point is that continental crust is constantly being recycled at the surface through erosion and sedimentation, but is rarely recycled back into the mantle. When continental plates collide, they're too buoyant to sink, so instead they crumple and fold, building mountain ranges. This is how the Himalayas formed when India collided with Asia, starting about 50 million years ago. The collision continues today, and the Himalayas continue to rise, though erosion removes material from the top about as fast as tectonic forces push the mountains up. Oceanic crust is very different from continental crust. It's thin, only about 3 to 5 miles thick. It's young, with no oceanic crust older than about 200 million years. And it's remarkably uniform in composition, made almost entirely of basalt and gabbro, dark volcanic rocks rich in iron and magnesium. The reason for this uniformity is that all oceanic crust forms in essentially the same way, at mid-ocean ridges where tectonic plates pull apart. Mid-ocean ridges are underwater mountain ranges that snake through all of Earth's ocean basins for a combined length of about 40,000 miles. They're among the most geologically active places on the planet, though they're hidden beneath miles of ocean water, so we rarely think about them. At mid-ocean ridges, two tectonic plates are moving apart, pulled by forces related to mantle convection. As the plates separate, hot rock from the mantle below rises to fill the gap. This rising mantle rock is under tremendous pressure from the weight of the rock above it. But as it rises and the pressure decreases, it begins to melt. About 20 to 30% of the rock melts, producing basaltic magma. This magma rises into the gap between the separating plates. Some of it erupts onto the seafloor as lava, forming pillows of basalt as the hot lava makes contact with cold seawater and quickly freezes. Some of the magma solidifies in underground chambers, forming layers of gabbro. The result is a layered structure of pillow basalts at the top, then sheeted dikes, vertical sheets of once molten rock, then gabbro, and finally at the base, partially melted mantle rock. This entire sequence is called an ophiolite. And when pieces of oceanic crust are thrust onto land by tectonic forces, geologists can study this layering directly. Once formed at the mid-ocean ridge, the new oceanic crust slowly moves away from the ridge like a conveyor belt, carried by the motion of the tectonic plate it's part of. As it moves, it cools, contracts, and becomes denser. Sediment begins to accumulate on top of it, the remains of microscopic marine organisms raining down from the water above. The farther from the ridge the crust travels, the older it gets, the colder it gets, the denser it becomes, and the thicker its sediment blanket grows. Eventually, after traveling across an entire ocean basin over tens to hundreds of millions of years, the oceanic crust reaches a subduction zone. This is where it meets another tectonic plate. And because the oceanic crust is now cold and dense, it sinks beneath the other plate and descends back into the mantle. As it descends, it heats up, and water trapped in its minerals is released. This water rises into the hot mantle above the descending slab, lowering the melting point of the mantle rock and causing it to melt. The resulting magma rises through the overlying plate and erupts at the surface, forming volcanic arcs like the Andes in South America, the Cascades in the Pacific Northwest, or the islands of Japan. Eventually, the subducted oceanic crust reaches depths where it melts completely and is reincorporated into the mantle. This is why no oceanic crust older than about 200 million years exists. It's all been recycled. The oceanic crust is constantly being created at mid-ocean ridges and destroyed at subduction zones, completing a full cycle in about 200 million years. This process, part of plate tectonics, is one of the key features that makes Earth unique among planets in our solar system. The boundary between crust and mantle is called the Mohorovičić discontinuity, or MOHO for short. It was discovered in 1909 by Croatian seismologist Andrija Mohorovičić. He was studying seismic waves from an earthquake that had occurred near Zagreb and noticed something puzzling. Seismometers at different distances from the earthquake showed two sets of arrivals for each type of seismic wave. There were the direct waves, traveling straight through the crust from the earthquake to the seismometer. But there were also faster waves that somehow arrived sooner, despite having to travel farther. Mohorovičić realized that these faster waves must have traveled down into a deeper, faster layer, where seismic waves traveled more quickly, then returned to the surface. By carefully analyzing the travel times, he calculated that there must be a boundary about 30 miles down, where the speed of seismic waves suddenly increased. This boundary, he concluded, marked the transition from crust to mantle. It was a profound discovery, providing the first direct evidence that Earth has distinct internal layers with different compositions. The moho isn't at the same depth everywhere. It's shallow under the oceans, just 3 to 5 miles down, because oceanic crust is thin. It's deeper under continents, averaging about 25 miles but ranging widely. Under mountain ranges, it can extend to depths of 50 or even 70 miles because the continental crust is thickest there, extending downward like roots. This variation in crustal thickness is called isostasy. Thicker, lighter crust floats higher on the denser mantle, while thinner, denser crust sinks lower. It's similar to how a large log floats with more of its volume above water than a small log. But both are floating according to the same physical principle. The moho itself is thought to represent a change in composition from crustal rocks above, dominated by silicates rich in aluminium, potassium and sodium, to mantle rocks below, dominated by silicates rich in magnesium and iron. This compositional change explains the change in seismic velocity. Mantle rocks are denser and transmit seismic waves faster than crustal rocks. Scientists have dreamed for decades of drilling through the crust to reach the moho and sample the mantle directly. In the early 1960s, a project called Project Mohole aimed to do exactly that. The idea was to drill through the ocean floor where the crust is thinnest. Between 1961 and 1966, several experimental drilling operations were carried out off the coast of Guadalupe Island in Mexico. The project successfully drilled through about 600 feet of ocean sediment and then penetrated about 300 feet into the basaltic oceanic crust, recovering core samples that confirmed the expected structure. But reaching the moho required drilling through at least another 2 miles of basalt, and this proved far more difficult than expected. The drill bits wore out quickly in the hard rock and had to be brought back to the surface frequently for replacement, a process that took hours. Keeping the drilling ship positioned precisely above the hole in the open ocean, where currents and waves constantly pushed it around, was challenging. As the hole got deeper, temperatures increased, causing the drill to overheat. The project costs escalated dramatically. Political support waned, funding was cut, and in 1966, Project Mohole was cancelled. For many years afterward, drilling to the moho seemed like an impossible dream. But technological advances have revived interest. Modern drilling ships have dynamic positioning systems that use GPS and computer-controlled thrusters to maintain position to within meters, even in rough seas. Better drill bits last longer. Improved drilling muds can handle higher temperatures. And there's still immense scientific interest in obtaining actual samples from the upper mantle. Several proposals for new mohole projects have been made. Some suggest drilling in places where tectonic processes have already thinned the crust or brought mantle rock close to the surface. One promising location is the Atlantis Massif in the Atlantic Ocean, where tectonic forces have exposed mantle rock on the seafloor with virtually no crustal cover at all. Another location is off the coast of Costa Rica, where the oceanic crust is unusually thin. A third option is to drill in the Indian Ocean, where the crust is also quite thin. In 2023, a new drilling project called the Mohole to Mantle Project began planning for an attempt to reach the moho sometime in the next decade. If successful, it would be one of the great achievements of Earth science, providing actual samples from the upper mantle that could be studied in laboratories around the world. These samples would help answer fundamental questions about mantle composition, the nature of the crust-mantle boundary, and the processes that occur at the interface between these two major layers. But even without samples, we've learned a great deal about the mantle through indirect methods. Let's continue our descent now, crossing the Moho and entering the mantle itself. Just beneath the Moho, about 30 miles down, if we're under a typical continent, we enter the uppermost mantle. The change is abrupt in some ways, but gradual in others. The chemical composition changes significantly. Crustal rocks are rich in silicon, aluminum, sodium, and potassium. Mantle rocks are still dominated by silicon and oxygen, which together form the basic building blocks of most minerals in Earth's outer layers. But the proportions of other elements are different. Mantle rocks contain much more magnesium and iron, and much less aluminium, sodium, and potassium. The dominant rock type in the upper mantle is called peridotite. This dense, greenish rock is composed mostly of the mineral olivine, along with pyroxenes and smaller amounts of other minerals. Olivine is a beautiful mineral when pure, ranging from pale yellow-green to deep green, and gem-quality olivine is called peridot. But in the mantle, olivine is usually mixed with other minerals and isn't gem quality. The chemical formula of olivine is magnesium iron silicate, and the ratio of magnesium to iron can vary. Mantle olivine is magnesium-rich, which makes sense because magnesium is lighter than iron, and lighter elements tend to concentrate in the outer layers of a planet, while heavier elements like iron sink toward the core. Peridotite is rarely found at Earth's surface because it forms under the high-pressure conditions of the mantle and is less stable at surface pressure and temperature. But in a few places, tectonic forces have brought mantle rock to the surface where geologists can study it. We mentioned the tablelands in Newfoundland earlier. This is a large expanse of peridotite exposed at the surface, brought up when an ancient ocean basin closed and thrust ocean floor and upper mantle rocks onto the edge of North America about 500 million years ago. The tablelands have a distinctive appearance. The rock is a dull orange-brown color from weathering. The landscape is barren, almost Mars-like, because the soil formed from peridotite is high in heavy metals like nickel and chromium that are toxic to most plants. Only a few specialized species can tolerate these soils. Streams flowing over the peridotite acquire a milky blue-green color from dissolved minerals. It's an otherworldly landscape, and walking across it is the closest most geologists will ever get to walking on the upper mantle. Scientists studying peridotite from locations like the tablelands have learned a great deal about upper mantle composition and processes. The rocks show evidence of having flowed, with minerals aligned in particular directions by shear forces. They contain tiny inclusions of fluids and minerals that provide information about conditions at depth. Chemical analysis reveals that the mantle is not perfectly uniform, but has subtle variations in composition from place to place, the result of billions of years of processes mixing and differentiating material. As we descend through the uppermost mantle, temperature and pressure continue to increase. At a depth of about 60 miles, we encounter an important transition. The rigid, brittle behavior of rocks gives way to a more ductile behavior. Above this depth, rocks respond to stress by fracturing, producing earthquakes. Below this depth, rocks respond to stress by flowing, slowly deforming without breaking. This transition defines the boundary between two important layers, the lithosphere above and the asthenosphere below. Lithosphere, meaning rock sphere, is the rigid outer shell of Earth. It includes the crust and the uppermost mantle, bound together into a single mechanical unit. The lithosphere is broken into about a dozen large plates and many smaller ones. These are the tectonic plates that move across Earth's surface, driven by forces related to mantle convection below. The lithosphere typically ranges from about 60 to 100 miles thick, though it's thinner at mid-ocean ridges and thicker beneath old, cold continents. The asthenosphere, meaning weak sphere, lies just below the lithosphere, extending from about 60 miles down to roughly 400 miles deep. Despite being solid rock, the asthenosphere is weak enough to flow over geological timescales. The high temperature, about 1,300 to 1,600 degrees Celsius, makes the rocks ductile. They can deform and flow in response to stress, much like glass, which is technically solid, but will flow very slowly if you wait long enough. The flow in the asthenosphere occurs over thousands to millions of years, far too slow to observe directly. But it's this flow that allows the rigid lithospheric plates above to move. The asthenosphere is a crucial component of plate tectonics. The plates don't move because they're sitting on a liquid. The asthenosphere is definitely solid, but it's weak enough that the plates can slide across it, pushed and pulled by forces we'll discuss shortly. Without the asthenosphere, plate tectonics as we know it wouldn't be possible. The lithosphere would be stuck in place, unable to move, and Earth would be a very different planet. As we continue descending through the upper mantle, the temperature continues to rise, the pressure continues to increase, and the minerals in the rock begin to change. At a depth of about 250 miles, we begin to enter a region called the transition zone, which extends down to about 410 miles. This zone is remarkable because the minerals here undergo a series of transformations driven by the increasing pressure. At normal surface pressure, olivine has a particular crystal structure. The silicon, oxygen, magnesium and iron atoms are arranged in a specific three-dimensional pattern. But at the high pressures found in the transition zone, this arrangement becomes unstable. The atoms can pack more tightly by reorganizing into a different structure. At about 250 miles depth, olivine transforms into a mineral called wadsleyite, which has the same chemical composition as olivine, but a different crystal structure. This polymorphic phase transition, as scientists call it, occurs quite abruptly and is visible to seismic waves as a discontinuity where wave speeds suddenly increase. As we descend deeper into the transition zone, approaching a depth of about 320 miles, wadsleyite undergoes another transformation, rearranging into an even denser structure called ringwoodite. Again, the chemical composition hasn't changed, just the arrangement of atoms within the crystal lattice. This second transformation is also visible seismically. These phase transitions are important for several reasons. First, they affect the density of the rock, which influences how the mantle flows and how seismic waves propagate. Second, they affect the physical properties of the rock, such as how easily it deforms. Third, and perhaps most intriguingly, they affect how much water the minerals can hold. Water in the mantle doesn't exist as liquid water, of course. The temperatures are far too high for that, and at these pressures, water would be in an exotic supercritical state that's neither liquid nor gas. But more importantly, the water in mantle minerals doesn't exist as H2O molecules at all. Instead, it exists as hydroxyl ions, OH-, incorporated into the crystal structure of the minerals. When a water molecule is incorporated into a mineral, it effectively splits apart, with the hydrogen becoming part of the mineral structure, while the oxygen may substitute for oxygen that's already present. Olivine, the dominant mineral in the upper mantle, can hold only small amounts of water, maybe a few hundred parts per million by weight. But wadsleyite and ringwoodite, the high-pressure forms found in the transition zone, can hold vastly more water, up to 3% by weight under the right conditions. This means the transition zone could potentially act as a massive reservoir, holding as much water as all of Earth's oceans combined, though locked into the crystal structure of minerals rather than existing as liquid. The question of how much water is actually present in the transition zone is one of the most fascinating and contentious issues in Earth science. For decades, it was purely theoretical. Laboratory experiments showed that wadsleyite and ringwoodite could hold water. But did they actually contain significant water in the real Earth? There was no direct evidence either way. Then, in 2014, a remarkable discovery was made. Scientists analyzing a diamond that had been brought to the surface by a volcanic eruption in Brazil found something extraordinary inside it. Diamonds form deep in the earth, typically in the upper mantle, at depths of 90 to 120 miles, though some rare diamonds, called super deep diamonds, form at much greater depths. As a diamond grows, it sometimes incorporates tiny inclusions of surrounding minerals, trapping them like insects in amber. The Brazilian diamond contained a speck of ringwoodite, smaller than a grain of sand, but unmistakable in its identity. This was stunning because ringwoodite had never been found on Earth's surface before. It had only been seen in meteorites, where it forms from olivine during the shock of impact. The presence of ringwoodite in the diamond proved that the diamond had formed at transition zone depths somewhere between 320 and 410 miles down. Even more remarkable, when scientists analyzed the ringwoodite using infrared spectroscopy, a technique that can detect the presence of hydroxyl groups, they found that it contained about 1.5% water by weight. This was direct, unambiguous evidence that water really does exist in the transition zone. The diamond had acted like a time capsule, bringing a piece of the deep mantle to the surface and preserving it in its original high-pressure form during the rapid journey upward. This single tiny inclusion, smaller than a grain of salt, confirmed decades of theoretical predictions and laboratory experiments. If the ringwoodite throughout the transition zone contains similar amounts of water, and if the transition zone is composed largely of ringwoodite, as models suggest, then the transition zone could contain roughly as much water as all the oceans on Earth's surface. This water isn't accessible to us, of course, but it plays a crucial role in how the mantle behaves. Water affects virtually every property of rocks. It lowers their melting temperature, which is why wet rocks melt more easily than dry rocks. It reduces their viscosity, making them flow more easily. It affects how they transmit seismic waves. It influences chemical reactions and mineral transformations. The presence of significant water in the transition zone has profound implications for understanding mantle convection, the generation of magma, the recycling of water between Earth's surface and interior, and the long-term evolution of the planet. Scientists now believe that water is cycled between the surface and the deep mantle as part of plate tectonics. When oceanic crust forms at mid-ocean ridges, seawater percolates into the hot rock, reacting with it and becoming bound into minerals. As the oceanic plate ages and cools, it accumulates a cargo of water locked into its minerals. When the plate eventually reaches a subduction zone and begins to descend into the mantle, it carries this water with it. As the plate descends, it heats up, and at certain depths, mineral transformations occur that release water. Some of this water rises into the hot mantle above the slab, triggering melting that produces the volcanic arcs we see at the surface above subduction zones. But some of the water remains trapped in minerals and continues downward with the slab. When the slab reaches the transition zone depths, the minerals transform into wadsleyite and ringwoodite, which can hold much more water. The water becomes stored in the transition zone. But the transition zone isn't the final resting place for subducted water. As slabs continue to sink and reach the base of the transition zone, near 410 miles depth, the minerals undergo yet another transformation. Ringwoodite breaks down into bridgmanite and ferropericlase, the dominant minerals of the lower mantle. These lower mantle minerals can hold almost no water. The water is forced out, creating regions of partially molten rock at the base of the transition zone. Some scientists believe this process of water release at the base of the transition zone creates a kind of water filter. Water-laden slabs descend from above, reach the transition zone, and release their water, which then becomes trapped there because the minerals can hold it. The now drier slabs continue into the lower mantle. Meanwhile, hot mantle rising from below reaches the base of the transition zone, encounters the trapped water, undergoes partial melting, and the resulting magma rises toward the surface. This water filter hypothesis is still debated, but it's a fascinating idea that connects many observations about mantle convection, volcanic activity, and the deep water cycle. Let's continue our descent now, leaving the transition zone and entering the lower mantle. At a depth of about 410 miles, we cross another seismic discontinuity, where ringwoodite transforms into bridgmanite and ferropericlase. This marks our entry into the lower mantle, which extends from about 410 miles down to about 1,800 miles, where it meets the outer core. The lower mantle is by far Earth's largest layer by volume, making up more than half of the planet's bulk. Bridgmanite is probably the most abundant mineral in Earth, comprising roughly 38% of the planet by volume. Yet, despite being so abundant, no one has ever seen a natural sample of bridgmanite from Earth. It only exists at the high pressures of the lower mantle, and if brought to the surface, it immediately transforms back into lower pressure mineral forms. This makes studying bridgmanite challenging. Scientists have only been able to examine it in laboratory experiments, where samples are squeezed to extreme pressures and heated to high temperatures to synthesize it. Bridgmanite has a perovskite crystal structure, where silicon and oxygen form octahedra that share corners, with magnesium and iron atoms occupying spaces between the octahedra. It's denser than the upper mantle minerals, which is why the transition from ringwoodite to bridgmanite is visible as a seismic discontinuity. The increased density at this boundary partly explains why the transition zone tends to resist flow between upper and lower mantle, though whether the mantle convects as a single layer or in separate upper and lower layers is still debated. As we descend through the lower mantle, temperature and pressure continue their relentless increase. At 600 miles depth, the temperature might be around 2,000 degrees Celsius and pressure around 250,000 times atmospheric. At 1,000 miles, temperature approaches 2,500 Celsius and pressure reaches 500,000 atmospheres. By the time we approach the base of the mantle at 1,800 miles depth, temperature rises to around 4,000 Celsius, and pressure exceeds 1.33 million atmospheres. The lower mantle is thought to be more chemically homogeneous than the upper mantle, but it's not perfectly uniform. Seismic tomography, the technique of using earthquake waves to create three-dimensional images of Earth's interior, has revealed large regions at the base of the mantle where seismic waves travel more slowly than expected. These anomalous regions are enormous, each roughly the size of a continent and several hundred miles tall. One sits beneath Africa, the other beneath the Pacific Ocean. Scientists call them large, low shear velocity provinces, or LLSVPs, though they're sometimes informally called superplumes or megablobs. What are these mysterious structures? Their slower seismic velocities suggests they're hotter than the surrounding mantle, perhaps by a few hundred degrees. But temperature alone might not explain all their properties. Some scientists think they might be compositionally different from the surrounding mantle, perhaps enriched in iron or containing ancient oceanic crust that has been subducted over billions of years and accumulated at the base of the mantle. Another intriguing idea is that the LLSVPs might be remnants of an ancient giant impact. The leading theory for how Earth's moon formed involves a collision between the young Earth and a Mars-sized body called Theia, about 4.5 billion years ago. This impact would have been utterly catastrophic, melting much of Earth's mantle and ejecting enormous amounts of material into orbit, which later coalesced to form the Moon. Computer simulations of this impact suggest that some of Theia's mantle might have remained in Earth's mantle after the collision, sinking to the bottom and never fully mixing with Earth's material. Could the LLSVPs be the remnants of Theia's mantle, still sitting at the base of our mantle billions of years later? It's a speculative idea, but it's consistent with what we observe. The LLSVPs appear to be long-lived features, stable for hundreds of millions of years, and they may play an important role in mantle convection. Hot mantle plumes, narrow upwellings of hot rock that rise from the deep mantle to the surface, seem to originate preferentially at the edges of the LLSVPs. These plumes create volcanic hotspots at the surface, like Hawaii, Iceland, and Yellowstone. The fact that plumes seem to come from the edges of the LLSVPs suggests that these structures are somehow involved in organizing deep mantle convection. As we approach the base of the mantle, we enter a thin but highly significant layer called D double prime, or D. This layer, only about 100 to 200 miles thick, sits directly atop the outer core. It's one of the most complex and poorly understood regions in Earth's interior. Here, the conditions are extreme, even by mantle standards. Temperature approaches the core temperature of 4,000 degrees Celsius or more. Pressure exceeds 1.3 million atmospheres. The heat flowing upward from the molten metal core creates a thermal boundary layer, where temperature increases rapidly with depth. The D layer has unusual properties. In some regions, seismic waves speed up or slow down in unexpected ways. The layer appears to be heterogeneous, with its properties varying significantly from place to place. Some areas show strong seismic anisotropy, meaning waves travel at different speeds in different directions, suggesting that minerals are aligned by flow. Other areas show reduced seismic velocities, possibly indicating the presence of partially molten rock. Scientists think several things might be happening in the D layer. First, it's probably a graveyard for subducted slabs. When cold, dense oceanic plates sink through the mantle in subduction zones, many of them may reach all the way to the base of the mantle and pile up in the D layer. These cold slabs would have very different properties than the surrounding hot mantle, which could explain some of the heterogeneity. Second, the extreme conditions in the D layer may cause mineral transformations that don't occur elsewhere in the mantle. Bridgmanite, under the special combination of temperatures and pressures found in the D layer, may transform into a post-perovskite structure. This post-perovskite phase was only discovered in laboratory experiments in the early 2000s. But seismic observations suggest it may be present in the D layer. The transformation from bridgmanite to post-perovskite could create some of the seismic discontinuities observed in this region. Third, chemical reactions may occur at the core mantle boundary. The molten iron of the core is chemically very different from the silicate rock of the mantle, and at the extreme temperatures at their boundary, elements might diffuse from one into the other. Some scientists have proposed that a thin layer of chemically distinct material might exist right at the core mantle boundary, formed by billions of years of reaction between core and mantle. The D layer is also where deep mantle plumes, those hot upwellings that create volcanic hotspots, are thought to originate. Heat flowing from the core warms the base of the mantle, creating regions where the rock becomes buoyant enough to rise. These plumes are probably not continuous streams, but rather episodic pulses of hot material that rise through the mantle over tens of millions of years. When they reach the base of the lithosphere, they create volcanic activity at the surface. Now we're ready to cross perhaps the most dramatic boundary in Earth's interior, the core mantle boundary, located about 1,800 miles beneath our feet. Everything above this boundary is silicate rock, compounds of silicon, oxygen, and various metals. Everything below is metal, primarily iron and nickel. The density change across this boundary is enormous. Mantle rock at the base has a density of about 5.6 grams per cubic centimeter. The outer core, just below, has a density of about 9.9 grams per cubic centimeter. That's nearly a doubling of density across a boundary only a few miles thick. Seismic waves behave dramatically at this boundary. P waves slow down as they enter the core, then speed up again. S waves can't enter the core at all because the outer core is liquid, and liquids can't transmit shear waves. This creates shadow zones on the opposite side of Earth from any earthquake. Regions where certain seismic waves simply don't arrive, because they've been absorbed or deflected by the liquid core. This observation, first made in the early 20th century, was how scientists first determined that Earth has a liquid outer core. The outer core is a churning ocean of liquid metal, primarily iron, with about 10% nickel and several percent of lighter elements like oxygen, sulfur, silicon, carbon, and perhaps hydrogen. The temperature at the top of the outer core is around 4,000 degrees Celsius, rising to perhaps 5,500 Celsius at its base. These temperatures are hot enough to melt iron at the pressures found in the outer core, though just barely. The outer core is close to its melting point, which means small changes in temperature or composition can affect whether it's solid or liquid. The outer core extends from about 1,800 miles depth down to about 3,200 miles, a thickness of about 1,400 miles. It's completely liquid and in constant motion. This motion is crucial because it's what generates Earth's magnetic field through a process called the geodynamo. Earth's magnetic field is one of the most important features of our planet. It extends far out into space, creating a protective bubble called the magnetosphere that shields Earth from the solar wind, a stream of charged particles flowing outward from the sun. Without this magnetic shield, the solar wind would gradually strip away Earth's atmosphere, as appears to have happened to Mars. The magnetic field has existed for at least 3.5 billion years, possibly longer, and has been essential for maintaining Earth's atmosphere and making the planet habitable. The magnetic field is generated by the motion of electrically conducting fluid, the liquid iron of the outer core. This is an example of a dynamo, a process where motion of conducting fluid in a magnetic field generates electric currents, which in turn create a magnetic field, reinforcing the original field. It's a self-sustaining process as long as the fluid keeps moving. The Earth's geodynamo is one of the most complex and poorly understood aspects of our planet's interior. What drives the motion in the outer core? There are two main energy sources. First, there's thermal convection. The inner core is hotter than the base of the mantle, so heat flows from the inner core through the outer core to the mantle. This heat flux drives convection in the outer core, with hot liquid iron rising from the inner core boundary, cooling as it approaches the core mantle boundary, and then sinking back down. It's similar to convection in a pot of water on a stove, but vastly slower and more complex due to Earth's rotation and the magnetic field itself. Second, there's compositional convection. The inner core is slowly growing as Earth gradually cools. As liquid iron from the outer core freezes onto the solid inner core, it preferentially crystallizes pure iron, leaving lighter elements like oxygen, sulfur, and silicon dissolved in the remaining liquid. These light elements are less dense and therefore buoyant, so they rise through the outer core. This process, called compositional convection, releases gravitational energy that helps power the geodynamo. In fact, compositional convection is thought to be the dominant driver of the geodynamo today, more important than thermal convection. Earth's rotation adds another crucial ingredient to the geodynamo. The Coriolis effect, the same force that causes hurricanes to spin and makes water drain in different directions in the northern and southern hemispheres, organizes the flow in the outer core into columns roughly aligned with Earth's rotation axis. These columnar flows, combined with the motion of the core material and the magnetic field itself, create a complex three-dimensional pattern that somehow maintains a predominantly dipolar magnetic field, meaning a field with a north and south magnetic pole, like a bar magnet. But Earth's magnetic field isn't perfectly stable. It wanders, fluctuates, and occasionally reverses. The magnetic North Pole isn't the same as the geographic North Pole. Currently, the magnetic North Pole is located in the Arctic Ocean, north of Canada, but it's moving at about 30 miles per year towards Siberia. This movement has accelerated in recent decades for reasons that aren't fully understood. The magnetic field also weakens and strengthens over time. Measurements over the past 2 centuries show that the field has weakened by about 10%. Most dramatically, the magnetic field occasionally reverses, with north and south magnetic poles swapping places. The geological record shows that reversals have occurred hundreds of times throughout Earth's history. The time between reversals is highly variable, ranging from tens of thousands to tens of millions of years. The most recent reversal, called the Brunhes-Matayama reversal, occurred about 780,000 years ago. We're currently in what's called the Brunhes normal polarity interval, meaning the field has the same orientation it has today. During a reversal, which takes a few thousand years to complete, the magnetic field weakens considerably, sometimes to just 10 to 20% of its normal strength, and the field geometry becomes more complex, possibly with multiple poles. The weakened field provides less protection from cosmic radiation and the solar wind, which could potentially affect the atmosphere and life on Earth's surface, though the exact consequences are unclear. There's no evidence that reversals have caused mass extinctions, but they might affect climate or increase mutation rates. Computer simulations of the geodynamo, run on powerful supercomputers, have successfully reproduced many observed features of Earth's magnetic field, including its general strength, its dipolar geometry, and even magnetic reversals. These simulations solve the equations of magnetohydrodynamics, which describe the behavior of electrically conducting fluids in magnetic fields. They're enormously complex calculations that can take weeks or months to run, even on the fastest computers. But they've provided tremendous insights into how the geodynamo works. One key finding from these simulations is the role of the solid inner core in stabilizing the magnetic field. The inner core acts like a stabilizing flywheel. The magnetic field permeates the inner core, and because the inner core is solid, the field there can only change on very long timescales through the slow process of diffusion. This provides a kind of memory that helps maintain the field's overall structure, even as the outer core undergoes complex time-varying flows. Without the inner core, simulations suggest that the magnetic field would reverse much more frequently than it does. Now, let's journey to our final destination, the inner core itself. At a depth of about 3,200 miles, we cross from the liquid outer core into the solid inner core. Despite temperatures that exceed 5,000 degrees Celsius, hot enough to melt any metal at surface pressure, the inner core is solid because the pressure at Earth's center is so immense. We're talking about pressures exceeding 3.5 million times atmospheric pressure, or about 360 gigapascals. At such pressures, the iron atoms are squeezed so tightly together that they remain locked in a solid crystalline structure despite the extreme heat. The inner core is a ball of solid metal about 1,500 miles in diameter. To put that in perspective, it's roughly the size of Earth's moon. But unlike the moon, which is made of silicate rock, the inner core is made of iron and nickel. The composition is thought to be about 95% iron, 5% nickel, and traces of lighter elements. The density at Earth's center is about 13 grams per cubic centimeter, more than twice the density of the rocks at the surface. The inner core is relatively young in geological terms. Scientists believe it began to solidify from the liquid outer core somewhere between 500 million and 1 billion years ago, as Earth gradually cooled from its formation. Before that, the entire core was liquid. The inner core has been growing ever since, slowly crystallizing at a rate of about 1 millimeter per year as more iron freezes onto its surface. This ongoing solidification releases latent heat, similar to how freezing water releases heat, and this heat helps drive convection in the outer core. The process of inner core crystallization is thought to be somewhat selective. Pure iron crystallizes preferentially, while lighter elements dissolved in the liquid outer core tend to stay liquid. These light elements become enriched in the liquid just above the growing inner core, making that liquid less dense and causing it to rise. This compositional convection, as we mentioned earlier, is a major driver of the geodynamo. The inner core isn't simply a uniform ball of iron. Seismic studies have revealed that it has structure and complexity. One of the most striking findings is that the inner core is seismically anisotropic, meaning seismic waves travel through it at different speeds depending on their direction. Waves traveling parallel to Earth's rotation axis, from North Pole to South Pole through the core, travel about 3% faster than waves traveling along the equator. This anisotropy suggests that the iron crystals in the inner core are not randomly oriented, but are aligned in some preferential direction. Why would this be? One possibility is that the flow in the outer core, organized into columns by Earth's rotation, exerts forces on the inner core that cause the crystals to align. Another possibility is that the way the inner core grows, with material being added at different rates at different locations, naturally creates aligned crystal structures. There's also evidence that the inner core may be rotating slightly faster than the rest of Earth, a phenomenon called superrotation. By comparing seismic waves from earthquakes that occur decades apart and pass through the same path in the inner core, scientists noticed small but systematic changes in travel time that could be explained if the inner core were rotating faster than the surface. The estimated superrotation rate is small, perhaps one extra rotation every several hundred to several thousand years. But if real, it's a fascinating consequence of the complex interactions between the solid inner core and the swirling liquid outer core around it. Recent research has suggested even more complexity. There may be an innermost inner core, a region at the very center of Earth with different properties from the rest of the inner core. Seismic observations hint at a boundary about 300 miles from Earth's center, where seismic properties change. Inside this innermost region, the anisotropy may have a different orientation, with fast-traveling waves aligned east-west instead of north-south. This could indicate a change in crystal structure or orientation that occurred at some point in Earth's history, perhaps related to a change in how the inner core was growing or in the pattern of convection in the outer core. The inner core also interacts with the geodynamo in complex ways. The magnetic field generated in the outer core permeates the inner core. In the solid inner core, this magnetic field is effectively frozen in place because electrical currents can't flow easily through solid metal, and any changes in the field can only occur through slow magnetic diffusion. This provides a stabilizing influence on the overall geodynamo, as we discussed earlier. Some scientists have proposed that the inner core might occasionally melt and re-solidify in response to changes in the geodynamo or in the heat flow at the core mantle boundary. If the magnetic field were to weaken substantially, the lack of compositional convection might cause the inner core to temporarily melt. Or, if heat flow from the core to the mantle were to increase for some reason, the outer core might become too hot for the inner core to remain solid. These are speculative ideas, but they illustrate how dynamic and interconnected all the processes in Earth's interior are. We've now reached the center of Earth, 3,900 miles beneath the surface where we started. Here, at the very center, conditions are as extreme as anywhere in our solar system outside of planetary cores and the interiors of stars. The temperature is estimated to be around 5,000 to 7,000 degrees Celsius, comparable to the surface of the Sun. The pressure is about 360 gigapascals, roughly 3.5 million times atmospheric pressure at sea level. Matter under these conditions behaves in ways that are difficult even for physicists to fully understand or predict. Yet from this distant vantage point, if we could somehow exist here, Earth would still extend 3,900 miles in every direction to the surface. We're at the heart of a vast, complex, dynamic system that has been operating for 4.5 billion years and will continue for billions more. Heat flows from this central region outward through the core, through the mantle, through the crust, and finally radiates into space. This heat flow drives everything: the convection in the outer core that generates the magnetic field, the convection in the mantle that drives plate tectonics, the volcanic eruptions and earthquakes at the surface. All of the processes we've described tonight, from the creation of oceanic crust at mid-ocean ridges, to the descent of subducted slabs to the depths of the mantle, from the flow of liquid iron in the outer core to the slow growth of the solid inner core, are interconnected parts of a planetary heat engine. Earth is slowly cooling, losing the primordial heat of its formation and the heat generated by radioactive decay. This cooling will continue for billions of years, but it's so gradual that we barely notice it on human timescales. Eventually, in the distant future, perhaps 2 or 3 billion years from now, Earth will have cooled enough that significant changes will occur. The mantle will become too stiff to convect vigorously. Plate tectonics will slow and eventually stop. The outer core may solidify, ending the geodynamo and allowing the magnetic field to decay away. Earth will become a geologically inactive planet, like Mars or Mercury, its interior cold and inert. But that future is so far away that it's barely conceivable. For now, and for billions of years to come, Earth remains a dynamically active, living planet. Our journey tonight has taken us from the thin crust we walk on, through the vast mantle with its slowly flowing rock, across the core mantle boundary into the liquid outer core, and finally to the solid inner core at Earth's center. Along the way, we've learned about plate tectonics, the water cycle between surface and deep mantle, the generation of the magnetic field, and the slow but inexorable cooling of our planet. We've seen how every layer connects to and influences the others, creating a complex system that has shaped the world we know. This knowledge has been hard-won, assembled piece by piece over centuries of careful observation, clever experiments, and logical reasoning. Ancient peoples could only guess at what lay beneath the ground. They imagined underground rivers of fire, vast caverns, mythological realms. The truth, as it turns out, is stranger and more wonderful than most myths. We live on the surface of an active planet, one that is constantly recycling its crust, generating a protective magnetic field, and storing vast amounts of water in mineral structures at depth. Understanding Earth's interior has practical importance too. Earthquakes and volcanoes, the most destructive geological phenomena, are surface expressions of deep Earth processes. Knowing how tectonic plates move and interact helps us assess seismic hazards and volcanic risks. Understanding the magnetic field helps us predict its future evolution and assess risks to technology from magnetic storms. Knowledge of mantle composition helps us understand the formation of economically important mineral deposits. And understanding how heat flows through Earth helps us locate geothermal energy resources. But beyond practical applications, there's something deeply satisfying about simply understanding the world we inhabit. We are thin films of organic material, living on the surface of a ball of rock and metal. Most of that ball is hidden from direct view, yet we've managed to map its structure, understand its composition, and comprehend its dynamics. This is one of the great achievements of the scientific method, using indirect observations and careful reasoning to understand realms completely beyond our ability to visit. As you prepare to rest now, you can take comfort in the stability and reliability of the Earth beneath you. The crust supports you. The mantle flows slowly beneath, as it has for billions of years. The outer core swirls, maintaining the magnetic field that protects all life. The inner core grows at the center, 1 millimeter at a time, year after year, century after century, eon after eon. These processes are patient and reliable, operating on timescales that make human history seem like a fleeting moment. The ground feels solid and still, but now you know it's part of something vast and dynamic. The seemingly static Earth is flowing, convecting, moving, changing, though so slowly that we perceive only stability. Mountains rise over millions of years. Ocean basins open and close over hundreds of millions of years. Continents drift across the globe, colliding and fragmenting. Magnetic poles wander and reverse, and beneath it all, the slow, steady flow of heat from Earth's center outward into space drives everything. You are safe on the surface of this remarkable planet. The processes in the deep interior have been operating reliably for as long as life has existed on Earth. They maintained the conditions necessary for life to originate and evolve. They will continue to maintain those conditions for billions of years to come. You need not worry about them. They function automatically, following the inexorable laws of physics, requiring no attention or oversight from you. So close your eyes now. Let your breathing deepen and slow. Feel the solid ground beneath you, that thin crust floating on the mantle, and know that you are held safely on the surface of a vast, ancient, patient system. The mantle will flow tonight without your awareness. The outer core will churn, The inner core will grow its daily fraction of a millimeter, and you can rest, secure in the knowledge that Earth, this remarkable planet, continues its slow, steady work. The journey we've taken tonight has been long, from the surface down through nearly 4,000 miles to the center and back. We've explored layers of rock and metal that you will never see directly, but that are as real as the ground beneath your feet. We've learned about minerals that only exist at extreme pressure, water stored in crystal structures where no liquid can survive, and metals flowing in patterns that generate invisible fields extending far into space. This knowledge doesn't diminish the wonder of Earth's interior. If anything, it enhances it. The reality is more complex, more interconnected, more dynamic, and more fascinating than anyone imagined before the development of modern Earth science. Every new discovery reveals new questions. Every answered question opens up new mysteries. The journey of understanding Earth's interior is far from complete, and it likely never will be. There will always be more to learn. But for tonight, we know enough. We understand the basic structure and the major processes. We appreciate the scale and the timescales. We marvel at the complexity and the elegance of how it all fits together. And now, with that understanding, we can rest. You have done enough thinking for today. You have traveled to the center of the Earth and back. You have learned what lies beneath the surface we walk on every day. Now, it is time to let all of that Earth knowledge settle into the background, to let the Earth manage its own interior, to let the ancient processes continue their patient work while you rest. The mantle will flow tonight as it flowed last night, and will flow tomorrow night, and for countless nights to come. The core will maintain the magnetic field as it has for billions of years. The inner core will grow its imperceptible amount as it does every day. These processes are automatic, reliable, eternal on any timescale that matters to us. They require nothing from you. So, sleep now, knowing that you rest on the thin surface of something vast and remarkable. You are supported by the lithosphere, protected by the magnetic field, kept warm by Earth's internal heat, and existing on a planet that is uniquely active and alive in our solar system. All of this exists beneath you right now, has existed long before you were born, and will continue long after you are gone. The ground holds you, the planet supports you, the universe contains you. And in this moment, that is all you need to know. Everything is as it should be. Everything is as it has been for ages. Everything will continue as it must, following the quiet laws that govern matter and energy. Let your thoughts fade now, like ripples on still water. Let your muscles relax completely. Let your breath become slow and even. Feel the weight of your body supported by the earth, supported by billions of years of geological processes that have created this moment, this place, this stable platform on which you rest. The earth is patient. The earth is ancient. The earth is vast. And you are held safely on its surface, a brief flickering of consciousness on a planet that will endure for eons. Rest now in that knowledge. Rest in the stability of the ground beneath you. Rest in the protection of the magnetic field above you. Rest in the warmth that flows from the core to the surface. You have traveled far tonight, down to the very heart of Earth and back. Now, you can release all of that knowledge. You can trust the planet to manage its own interior. You can simply be here, on the surface, safe and supported and protected. Good night, and sleep well.